from the European Bioinformatics Institute, who will be talking about connected life sciences data approaches there.
Okay, thanks James. Thanks for inviting me to talk. So I'm going to give you a sort of little bit of a historical perspective on bioinformatics. So and kind of ending up with sort of stuff that's a bit more appropriate for this. So if I start off, I'm the technical coordinator in the samples, phenotypes and ontologies team. We do an awful lot of helping people structure their data a little bit better to make it more integratable within the institute. So first of all, I thought I should outline a bit about who we are. So what is MBI? Anybody heard of us before? A few people. So several of the people who actually work there. We're basically Europe's home for biological data services. We do some research and training, and we're a big data provider for life sciences. There's 570 members of staff or thereabouts from 57 different nations. We're part of EMBL. We actually predate the European Union, EMBL. It's a Europe-wide treaty organisation. So we dodged a Brexit-shaped bullet. And our mission really is to provide freely available data and bioinformatics services to all facets of the scientific community. So we deal with a lot of kind of archiving of data, representing of data, and analysis of data in the biological context to scientific researchers. This is us. We have a lot of data, a lot of web hits. So we get about 18.5 million requests to our website every day. The scientists at over 5 million unique sites. We have tons of data. We're not NASA, but we're quite important, I think, in our field. A little bit about biology. We're going to start with a little bit of a lesson. So hope you've got your thinking caps on still, even though it's just 4 o'clock now. So biology's changing. There's much more data generation happening with genomic sequencing. There's more data, more variety of data. There's a bigger emphasis on systems biology, so everyone's always after the next big drug. How do I identify the next target that I'm going to be able to create a new medicine for? And we enable a bunch of of areas in different fields, so molecular medicine, agriculture, food. There's a huge range of a number of applications. So how does this actually apply to this conference? So first of all, a bit of high school biology. Anybody remember this? No? Okay, good. I'm glad they included this slide then. So this is actually from Wikipedia. This is the central dogma of biology. So basically this is saying, okay, I've got a DNA molecule that's transcribed into RNA and that produces proteins. High school level biology, but this is graph, right? Nice simple one, but it's a graph. And at some level, all of our data kind of has this assumption built in. Not quite that simple, unfortunately. So this is also from the same Wikipedia page, slightly more complicated view on the same bit of biology. So we have DNA actually replicated, transcribed into RNA, proteins. The green arrows here are the but what about moments. So, and these happen all the time when you're trying to model real biology in data. So you get reverse transcriptases, that you've got different enzymes that control replication. So there's a bunch of these all the way out. We go from a simple worldview to a bit more complicated, all the way up to all the way up to systems views on the data. So in this case, we've got protein-protein interaction pathways and variable gene expression in different tissues. So essentially, these first few slides are biology is quite complicated when you try and represent it in the data. But all of these things are graphs as well. So that's kind of the take-home message. So this feeds into the way that we structure the resources at the EBI. These are some of the data resources that we have, all the way down from the very molecular level, genes, genomes, variation. This is molecular biology, all the way out to systems biology, and these sort of represent clusters of bunches of different resources here. And each one of these services serves as a resource with its own kind of database, its own kind of data representation, its own data modeling. The blue box on the left is kind of highlights the ontologies that we use to structure the data. So, and my team are fairly heavily involved in this kind of aspect of work. So, we use these ontologies to provide consistent vocabularies over the data, and they link into each of the services in turn. So, and this is a view of how those databases actually interact with each other. So around the outside of this wheel are the resources that we saw on the previous slides, and the lines between them represent interactions or data exchange or cross-links between those databases. So, so I think the point of this slide is that in bioinformatics, we're actually really good at making links between different pieces of data, different resources. We cross-link heavily, and we've actually been trying to do this for like 20 years. So. We spend a lot of time kind of importing data, cross-linking, building bespoke pipelines to link these things together. So really, we've been connecting data without doing linked data for a long time. So how do we just expand that a little bit further? So this is a view on part of a project that we recently built that I'm going to come on to. The green boxes here represent a sort of subset of those resources that we've been looking at, and the blue things are the entities that represent consistent terms within them. So you've got genes and proteins in here, two different views on proteins in these two different databases, and the links between them. So if the previous slides that we saw are sort of like biology 101, this is kind of bioinformatics 101 as well. So you won't normally get through a bioinformatics master's without trying to do, at some point, without downloading at least a couple of databases and combining them into a new one. So what we're talking about here is trying to formalize this process a little bit. And we actually get quite good at doing this. So this is the log cloud, the pink bubbles here, and these ones are life sciences linked data. So these are kind of RDF data sets, and they're heavily interlinked. So most of those databases that we've seen produce at some level, or have produced at some point, a linked data view. So it's a natural extension for us to take that kind of wealth of knowledge, those wealth of links, and build the RDF platform. This is a resource that we built at UBI, where we essentially took all those RDF views and put them into a triple store and offered up a front end and Sparkle endpoints to them all. So we do RDF. So a couple of questions, couple of challenges with that. Did we want to model the data that we're representing, or the real biology? So we used RDF because we can type it. So the typing and semantics is the main strength, and there's a lot of ontologies that we wanted to take advantage of. So we built formal data representations, link them to ontologies. But most of those ontologies model the biology of the situation. The RDF platform captures the data. So there's a question here about what an entry ensemble, which is one of our data resources, what does that represent? Is it actually a gene, or is it a record about a gene? So there's some questions and some challenges. So just to expand on that a little bit, database entries or real world entries. In all practical sense, it isn't reasonable to, or isn't sensible to treat them as different things. So we made the database entries proxies for the real world entities. Doing this any other way would introduce a layer of indirection. It makes it harder to query, makes it harder to make sense of, and we can use biologically meaningful representations, relationships of these things to sort of query across. So, without trying to kind of load too much into this. So, but this is still a use case driven approximation, right? So, how strict do we want to be? You kind of, at some level, you're going to assume that when everyone's talking about this thing, they're talking about the same thing consistent. So we do get a little bit away from this, but just to wrap up these kind of challenges. So the semantics in the data that we have is actually quite complicated. That each of our resources, each of the things on this diagram here, hide, each of these green boxes actually hide quite a degree of complexity. So they each have their own schema. They're each kind of fairly deeply involved, and they change all the time as well. So So capturing that semantics consistently is actually very difficult. You have to kind of defer to each of the individual resources where the expertise lies and try and integrate on the touching points. But of course, doing that makes it even harder to represent a provenance model. So now we have a bunch of databases that are all releasing at their own schedule. We have to pull in new versions when they exist and somehow capture the fact that this is somehow related to the latest state of the art. The relationships between the data are hard to define, so we see an awful lot of cross-references without any knowledge of or any specific kind of examples of what that really means. And our understanding of each of these resources can change rapidly. So this is the other thing about biology, is schemas are never fixed in stone, right? So one finding can throw your current state-of-the-art understanding out of the window, and each of those individual resources have to be able to react and say, okay, we need to redesign how our schema works. And this is especially true in the new sorts of technologies. So new higher throughput sequencing methods give us the ability to make findings much faster than we ever had before, and that changes our understanding faster. And this is the big thing, I think, balancing the use cases, the queries that the users want to do with the representation is a major challenge. So the harder you try to get your representation correct, the more precise you make your modeling, the more you make it accurately reflect the biology, the harder it becomes to query, and the harder it becomes for any one person to understand it, because now you've got very fine details about every resource at the EBI, which there's 570 people trying to work on. So the deeper you go, the harder you model it, the harder it becomes to query it. Now this might be useful for some use cases, but is very bad for simple query cases. So just to give you one concrete example of this is one way in which there's one gene connected to one protein in our RDF platform. So we did this analysis to try and see, okay, what's the sort of shortest path to get from this gene to this protein, hoping that we get a nice clean picture in alignment with that central dogma slide that I showed you before. What you actually get is this. It's a giant hairball. So just to change tack a little bit now. So I think what I've shown you so far is that we've got a lot of data, and we invest a lot of effort in trying to capture and make explicit the semantics of that data in order to put it into an RDF platform and offer Sparkle queries over it. We also go the other way, just to completely throw things out of the window. So this is the space of ontologies in the life sciences. There's an awful lot of ontologies that are awfully heavily used in a lot of different places to annotate data, to type data. And at the EBI, we've actually recently built a service using Neo4j to represent this. So I'm going to talk about that very quickly. Ontologies as graphs. So I think we've kind of covered this today. So there's a crossover between these two things. So although our ontologies aren't graphs, you can flatten them out as an RDF graph. People quite often want to query them as if they're a graph. And that's kind of a really interesting angle for us. So there's plenty of RDF databases around, but if you're not actually using the semantics of these things, then or not actually trying to do any inference on these things, then actually do you need to use RDF for that? So these were our use cases for the ontology repository that we wanted to build to capture the sort of search domain over all those ontologies that existed before. So these are the things that people want to be able to do, right, with that body of ontology. They want to be able to search for ontology terms. They want to be able to query the structure a little bit, like by getting parent and child terms. Maybe the transitive closure, so get me all the types of this thing. And query across some relations, like give me all parts of the cardiovascular system. And actually, all those things we can really easily satisfy using Neo4j, right? So we built this service backed by Neo4j. It's a repository of 150 ontologies, and you can check this out. The URL's here, and the code's all in GitHub. So what we did is we took the ontology. Basically we wrote an OWL to Neo4j converter, and we pulled out all the things that all the classes in the ontology, but also properties and individuals, and labeled, created a node and labeled them, and index the relations between these things as well. So you can build up this kind of graph, and that gives you the ability then to basically do some fairly fairly powerful but fairly simple query. So if a user comes along and says, "I want tell me all the transitive closure, so all the types of a heart, following the parent and partonomy relations," you do this kind of query, and we get this kind of view in the interface. And this gives us the ability to do this kind of subsumption querying and build this into search indexes. So I will finish there. Some final thoughts. So this is just this is a bit of a brain dump about the sort of things that bioinformatics have been doing with RDF data, with graph data, and I think basically the moral here is that we've been trying to put data links together for at least the last 20 years to show any value here. Given that all these kind of pipelines, all these cross-references in databases exist, you either have to be able to do something new, so make a finding that wasn't possible before, or to do something better, or faster, or easier, or cheaper. And for us, I think RDF and Neo4j, they're two ends of a spectrum, right? So it boils down to how deeply you want to model things. So if you really need a deep semantic representation, you really want to explicitly capture the semantics of things, then do it in RDF. There's good technologies. That's great. You can build an accurate representation, but you have to be aware that might be difficult to build and difficult to query. So you need to be able to show a value proposition of doing this. And also, what are your scenarios for inference? What are you going to do with those deep semantics? On the other hand, if you've got some fairly simple query use cases that you can easily define, it's much quicker and easier to build a graph in Neo4j, and there's great tooling support. You can very quickly build websites on top of it, and it's easier to query. So that's kind of all I wanted to say. This is the obligatory acknowledgement slide, citing funding stuff, and I'll take questions, I guess. Thank you.
Thanks very much, Tony.
So you said it was easier to do it in Neo4j, but I mean RDF triples and Sparkle are not that difficult. How is it easier? What actually made it easier?
So I think our experience is we found it easier to generate the data formats to load into Neo4j, rather than you need quite a lot of understanding and the tooling support to be able to accurately generate a rich RDF description. It's kind of hard, right? And you have to agree these concepts between. And in our case, excuse me. In our case, we were agreeing kind of concepts and touching points across a wide variety of resources. Getting people to use consistent terminologies in the same way is kind of difficult. Now that problem doesn't go away if you do it in Neo4j, but it's kind of the barrier of the consequences of getting it wrong are kind of a little bit lower, because it's not like you're trying to aspire to some sort of global standard, get your semantics exactly right across all scenarios. So that was our one finding. The other facet to that is that the amount of code that we had to write to offer the Sparkle endpoints and query interfaces and visualizations over a triple store, we used that Virtuoso to back the RDF platform, and to actually build anything on top of that, we had to write a lot of code. And the tooling support for Neo4j is great. We had to write a vanishingly small amount of code to build the ontology lookup service. So that's the answer.
Okay. Any other questions from the room? No? Okay. Well, thanks very much, Tony. Really interesting speech.